recording. So final bits of 2D, plain old 2D integration. Also today we're going to go through the final part of rational integrals, and then we're tomorrow going to do improper integrals, and that's the all of theory for this period and just about time. So this is kind of a continued from the previous lecture. So now when we're having, we are calling this method of partial fractions. In the textbook, it's roughly 366. We're not going through all the examples, but I hope that we're doing a bit more on the parts where the textbook says that, okay, this is kind of obvious that this follows. So when you see in a math textbook, a note that from this follows this. If it is not very obvious to you, that's kind of a passive-aggressive hint that you should practice a bit on how to do the manipulations. So an additional trick for solving these P over Qs, which we last time did by just calculating a quotient and using that to then solve the integral. Then maybe we can factor the denominator instead, and we get something of this form that we can divide the P over Qs to such a form that on the numerator we have only constants, which are commonly marked with A1, A2, and so on, or A, B, C, D, and so on. And then on the denominator, we get only low degree polynomials. This example here shows that there's only linear functions, so x minus a, a1, x minus a2, and so on. But it is possible that you will get second degree functions on the denominator as well. But if you get on linear, then these non-capital A's are based on the roots of the polynomial Q. So how do we find capital A's? So the non-capital ones we could find as the roots of the polynomial Q. How do we find the A constants or ABCs? So one method is that we essentially add up most factors or multiply with the denominator of the A in question, and then get a system of equations. No, this was a add up factors part. Yeah, we get a system of equations there. And then we can solve that. We are going to talk later about how to solve larger systems of equations. So that's kind of a little logical jump, but this should be familiar to you. So how many of you can remember that you have had some talk about system of equations, or in Finnish yhtälöryhmät? Okay, a few. We're going to have an example of that, a simple example then. And then the second method is we multiply all terms of the denominators, so of what you want to solve. So if we have A, J here to solve, then we multiply everything else with x minus aj. So what was the denominator of A? And then we can add up the rest of the terms and solve for aj. And when we take the limit where x approaches aj, we should get the value of that. What this actually means, so let's take this kind of a function. We want to integrate that, and we're going to show both methods. The factor of the denominator, well, we could solve the roots otherwise, but we can rather easily see that it's going to have this kind of factorization. that's standard form. So x minus 2 times x minus 3 is going to be x squared minus 5x plus 6. And we're supposed to get two constants. So if you're having a small number of constants, it's probably easier to mark them A and B. So there's less chance of mixing up that which A this was. Unless you get something really weird on naming scheme. What naming scheme you use doesn't really matter for an acceptable solution, as long as you don't get mixed up easily. So we'll have a look. To method 1, we're gonna multiply back. So what happens here is we have multiplied these A's and B's here with the opposite denominator. So we're getting back to the original denominator. So A was multiplied by x minus 3, well, x plus 3 here. Wait a moment. Oh, I got this right. Yeah, well, it should be x minus 3, and then B was multiplied by x minus 2. This is the problem of using ready examples, is that I'm getting a small wait a moment thing here. Anyway, here we can see that the denominators are the same, and for these to be equal, these two functions, then the numerators must also be the same. And for the numerators to be the same, we know that there is the constant of that numerator function must be the same. So let's put in x equals 0. We get 4 must be 3a minus 2b. Yeah, there's a wrong sign here. It should be minus 3a. So I've got a typo right over here. This one should be a minus. This plus here, it should be a minus. Then it makes sense. And also, now we've got that constants are minus 3a minus 2b. And then the multipliers of x must also be the same. What's the multiplier of x here? It's 1. So 1 must be equal to a plus b. So we do get this system of equations. Now let's have a look at how to solve this thing. So okay, that's far. Well, never mind. So I'm going to just remind myself what it was and how to do these kind of solutions. So this notation means, well, a bit too large. This notation means that both of these equations must hold to get an answer. So we have 1a plus 1b equals 1. And we have minus 3a minus 2b equals 4. And we can, when we're solving these kind of equations, we can change the order of the rows without changing anything. So that's just a logical AND, so everything must hold. By the way, if you ever end up having a logical OR, it would be marked with a square bracket. So this is AND, everything must hold, and this is OR, at least one must hold. And we can also multiply rows, and we can add rows together without changing the answer. So those are three three things we can do, which will formally swap rows multiply rows and add rows. Now, of course, when we have multiplication and addition here, we can also add multiples of one row to another row. So that's both combined. Now, when we want to solve things, then we'll need to figure out how we can eliminate. So this is called Gauss elimination. We're going to talk more about it later. This is kind of an important basis of linear algebra. So what we're going to do here is we are going to, so we name usually Roman numerals. This is row 1 for the first row, this is the second row. Now I can tell here that I'm going to add 2 times the first row here. So I'm then going to end up having technically still a 1a plus 1b equals 1. And then I add twice of 1a, so 2a's to minus 3a. I get minus 1a. I add 2 1b's, so I add 2b's to minus 2b plus 0b equals, I add 2 times 1 to 4, I get 6. Okay, this is cancelled, so now we have the result that minus a equals 6, or solving for a is at this point relatively trivial, a equals minus 6. So this is called a triangle form. So when we have cancelled out that part, we should end up having a triangle. So we do, now when we solve one, we can then put that solution of a equals minus 6 to the next above. So here we have only 2 functions, but we could have an arbitrary number of functions. And actually, we do need at least the same amount of functions than we have unknowns to solve this kind of a system of equations. Or then we're going to have infinite amount of solutions because we're going to have unsolvable functions there left. So now when I put into 1a, so now I here substitute a equals minus 6 here. I get minus 6 plus b equals 1. Move minus 6 to the other side, we get b equals 7. And these are going to be our solutions. So we could now solve this system of equations, and the solution we get is a equals minus 6 and b equals 7. So that's a simple example how to solve system of linear equations. Usually those are a bit larger. We're going to go through that on period 2. If you use MATLAB, then there's a ready-made command of solving system of equations with the backslash operator. The method number 2 is canceling out parts. So if everything works fine, we should be able to multiply the denominator of a, and then we can cancel out that part by setting x equals 2. So what we get is the common numerator, which is here x plus 4 in our example, and then to multiply denominators of the other constants. Now when we have only one other constant here, so we have only two unknowns to solve, then a equals the common numerator divided by the denominator of b. And we put in x equals 2. We get 2 plus 4 is 6. 2 minus 3 is 1. 6 over minus 1 is minus 6. And that's our a. And then x plus.
Sorry, but the screen share is not on.
Oh, thanks. Good. Now where's my Zoom? Okay, here. Okay. Did we miss anything? Yeah, no. So we could solve that and get answers. And yeah, here, method 2. So what I just said, x plus 4 is the common denominator from here. Or well, we can have it here as well. And then the common numerator, yeah, and then the denominator from the other. If we had more than two unknowns, then we would need to multiply all the denominators and still use the common numerator. And t is just substitute the x value, which sets the denominator of a into 0, and we get the values. So minus 6 and 7. And then the final part is substituting back to integral. So we have this a over some function plus b over some function and so on. So we can divide at the addition. So we can solve the integral one part at a time. And of course, we can take the constants out of the integral. So we end up having 1 over some function, which we can reduce to this elementary integral. It should end up having logarithm. So in this case, minus 6 times logarithm of absolute value x minus 2, and so on. And plus c. So two methods, and whichever of these appears to be easier. So if it's really easy to factor t's, well, okay, both require factoring. Then if you're really familiar with solving linear equations, this is probably easier. And then this maybe with more complex systems, this requires more algebraic manipulation, perhaps, but 10 is relatively foolproof at that. And 10, what happens if we're having something we cannot factor? For example, here we could go to the linear factors. We get that we have x times x squared plus 1 in the denominator, and that's as far as we can go. And we do have then another form of these similar decompositions. So we have a over x and some b times x plus c over x squared plus 1. So we then do the decomposition at the parts we can. Now, if you try to figure out how would we get back to the original function from an assumed x, so we assume that this form of a over x plus bx plus c divided by x squared plus 1. So we assume this exists, and now when we multiply back to get the original form, the denominator must be x times x squared plus 1. So the multiplier of a must be x squared plus 1. And then we must multiply bx plus c with x. And this must be equal to what we have here on the original numerator. We can here see that the quadratic term appears in a and b. So a plus b must be equal to 1 because the original one, our multiplier for the quadratic term, x squared, is 1. And then c must be the linear constant because we have x times c here. There are no other linear parts, so we can solve this system. It is also a system of equations. So c must be 3. And then a, well, because a is the only one here that has just a raw constant, so a times 1 appears here, so a must be equal to 2. Now we know that a is 2. We can solve a plus b being 1. So if a is 2, then b must be minus 1. So we could then solve these, and now we can split the integral at this part and integrate separately 2 over x, and then we can integrate this using the methods we learned last week. So try doing quite a bit of work to then get in a slightly simpler to solve form. Technically, we could try some rules. There are also probably textbook rules how to get so if you have the handbook, you can also use the handbook to check the formula there, which probably saves some time, unless the problem tells you that you must use a specific method. So the general theorem is that we have some quotient p over q, where p and q are polynomials, where the degree of p is smaller than the degree of q. We assume that qx can be fractioned, and in some cases we may have quadratic or higher fractions. So ideally we have only those x minus a's, but we may also have these x squared terms appearing here. So we may have also fractions of this form. If we sum all the m's and double the m's, so here's our x squared, so this is quadratic part. So if we look at the original degree, then these constitute 1x, these constitute 2x powers. So for example, here the original degree is x cubed minus x cubed plus x. So it's third degree function. We will get the degree of q. And we assume that this p over q can be expressed as sum of quotients with constant multipliers and the aforementioned fractions as denominators. And then once we can find that form, then we can, in a bit more easy way, integrate those functions. And that was quite a lot. I should probably still work out a few more examples, so you have a bit more to work on. Our next topic is improper integrals. And at this point, my material still has things like insert example here. So we're gonna go through this tomorrow morning when I have had some more time to actually work those examples out myself, because I ran into a little block there. Wait a moment, what is the textbook writer doing over here? Any questions at this point? At least none on the classroom. So I don't know about your customs, but in Finland it's almost lunchtime. All right. I'll also have some homework. I got some feedback that it came as a surprise to some last week that it wasn't due Wednesday night. So let's say that anyway, our homework will be. Hey, wait, next week is exam week already. Okay, then you're going to have 2 weeks of time to do the homework. So it will not be due next week. It will be due the week after. Essentially, it will. The idea is that we're going to go through the homework in class. So what were the solutions if not everyone was able to solve everything? Then that way it doesn't make sense to demand that you return it early when we haven't shown the solutions yet. Also, reminder, if you're running out of time, you can tool allows you to return multiple files. So if you worry that can you solve everything in time, then Radar submit in multiple files, even when I ask for one file, so you have something returned, so that you don't lose your work kind of compared to. So reminder is that homework is part of our course completion. It's supposed to reward you for practicing, and also when we get some more challenging problems, also kind of check on how difficult problems you can solve mostly on your own. Of course, you can also discuss the problems with each other, and I hear you have been doing that, which is great. But at this point, I guess time to stop talking, and this is it for our lecture. And this time I'll try to upload it a bit sooner than I had the last few ones.